Google's not being tech savvy. All right.
Teaches you how to use it.
Yeah. So in any case, what I have here is two 2-liter bottles side by side to show you one's going to react and one isn't. And we're going to see if this reaction is exothermic. You guys remember what exothermic means?
Yeah.
Okay, it means that something is giving off energy. We're going to learn today that giving off energy is a net change. There's energy that has to be absorbed also, and there's energy that's also released. Okay, so in this reaction, when we see any reaction that gives off energy, okay, it's because there's a net change, and I'll talk about that when we get to the lecture part. But in any case, overall energy is going to be released here. Let's see if we can see any evidence of that. I'm going to take some hydrogen peroxide. This is 30% hydrogen peroxide. Okay, you guys in stores have 3 or 6%. So I'm going to start with about 30% hydrogen peroxide. Okay, and now what I'm going to do is right now this is decomposing, okay, into oxygen gas, okay, and also water vapor. Hydrogen peroxide, you have to keep the bottle on tight because it'll become water over time. It's a mixture of water and H2O2. That's the molecule it's decomposing. So my friends in chemistry, right now it's breaking down into water vapor, okay, and O2. Bonds are being broken, okay, and also we're reforming new bonds. Now, I'm going to speed up the reaction with a catalyst, manganese dioxide. So it's happening now, but happening at a low rate. By putting a catalyst, I'm speeding it up, and we're going to see the effects of the decomposition and the exothermic reaction. So here we go. Remember the I Dream of Jeannie show that used to be on? Now what's happening to the bottle if you watch carefully?
Shrinking.
Yeah, look at its label. It's kind of like it was at a size 3 dress and now it's a size 0. Okay, if that makes any sense. This is now a tube top. Okay, I think we can do some more. It looks like to me that it's still working its magic. So let me add some more catalyst here. Okay, and we can see that that is oxygen vapor and water vapor being produced. And again, very exothermic because the bottle is shrinking. So they can tell that the heat is being released. Okay? All right. In fact, still like there's still some more. I think this catalyst here is not so great. Here we go. Now we're talking. And that's the decomposition, all right, of hydrogen peroxide into water vapor and oxygen. Very exothermic. You can see that clearly that the bottle to the right is much, much smaller. Okay? You can see that the label doesn't fit anymore. Lost too much weight. All right? And we'll stop there.
In today's video, we're going to identify and state chemical equations for the decomposition of compounds. So here's a compound, and we are decomposing it down into its elements. We can, if we sort of think back to synthesis reaction, where we took 2 elements and created a compound, you can see here that this is sort of the opposite. You start with a compound and end up with the elements. So we're actually just doing exactly what we did before, just backwards. So in terms of a definition, it's a reaction in which substances are broken down, and it is the opposite of a synthesis reaction. If we're going to identify if a reaction is decomposition, what you're really looking for is it compound, making an element in an element, or is it a complex compound being broken down into several simple substances? So let's take a look at a couple examples of what we mean there. For example, here we did this reaction where it's called elephant toothpaste, and what would happen here is the hydrogen peroxide is decomposed into oxygen and hydrogen. In the example here of a complex compound, here's vinegar being decomposed into methane and carbon dioxide. So those are 2 examples of decomposition reactions. Now let's talk a little bit about how do we actually predict their products. So the first thing we need to do is we need to write each element separately. So let's start with an example and talk about what we mean. So if we want to see what is a decomposition reaction for ammonia, we need to start by running each element separately. In other words, it's going to break down into nitrogen and hydrogen. Then we need to add any subscripts for our exceptions. So we know that nitrogen and hydrogen both need a 2. And then we do our balancing at the end. So exactly similar to what we were doing before. If we had something like glucose, it breaks down into carbon, hydrogen, oxygen. And hydrogen and oxygen need subscripts, carbon does not, and then we can balance to make sure that we have 6 carbon, 12 hydrogen, 6 oxygen, 3 times 2, 6 oxygen. Now both of those are covalent compound examples. It also works for sodium chlorides, which is salt, which is an ionic compound. It's the same thing, it's going to break down into sodium and chlorine. We have to see which ones need subscripts, chlorine does. And then we need to balance. So we see here we have 2 chlorines, but only 1 on the left hand side, so we're going to have to multiply by 2, and then we need 2 sodium, and now we're all balanced. So those are how we approach those 3 steps to predicting the products of our decomposition reactions.